Hey guys, welcome back. Day 31. We're talking about electrolysis today and Faraday's law of counting electrons, possibly corrosion in this video. Let's dive in with electrolysis. So, an electrolytic cell. This is when an electrical current drives an otherwise non-spontaneous redox reaction. E standard for the cell would be negative, and the reaction that occurs will be the easiest one. And the easiest one is the one with the least negative standard cell potential. So it's kind of backwards from a voltaic cell. Now, in all electrochemical cells, the oxidation occurs at the anode, and the reduction occurs at the cathode. So that's every electrochemical cell, whether it's a voltaic cell or electrolytic cell. For voltaic cells, these are the spontaneous cells, where E standard should be positive. Right? The anode is the source of the electron and is negative. Anode is the source of the electrons and is negative. That's where the oxidation occurs. The cathode is, well, not is, draws electrons to itself and is positive. So that's where the reduction happens. In electrolytic cells, so the electrons are drawn away from the anode, which must be connected to the positive terminal of the external power source. So the anode is now positive and still oxidation. And in this case, electrons are driven to the cathode, which must be connected to the negative terminal of the external power source. So the cathode is negative, and it's still where reduction happens. Let's look at a picture here. So we have a voltaic cell and we have electrolytic cell. This is on the left, the voltaic cell where we had zinc and the electrons starting on zinc here, zinc metal, going to copper metal, and that's what we talked, and it just spontaneously happens. In the electrolytic cell, we have what we call an over potential, where the electrons are being driven to the cathode. And so that the electrons, basically the circuit goes the other way. It's basically the other way. Now the cathode here is, so they switch signs. So the cathode is still the negative terminal. That's where the reduction is happening. The anodes, right? So copper is actually being oxidized to copper 2+, and zinc's being reduced to zinc. So that's the difference. Voltaic cell, electrolytic cell. Voltaic cells are spontaneous, how the electrons want to go. The electrolytic cell is non-spontaneous, how we want the electrons to go most of the time. So now let's talk about something we would want to do. Potential would be the electrolysis of water. And the goal would be to produce H2 gas. And that would be a nice goal, wouldn't it? So we'd have fuel, basically. So for water to actually conduct electricity, you would need an electrolyte in there. And the electrolyte, let's just common one example, a dilute solution of sodium chloride. Okay, so then that leads us to the questions. What species are in the solution? And then what is oxidized? And what is reduced? Good question. So let's talk about the reduction at the cathode. So let's define our species real quick. So I have Na plus Cl minus, and I would have H2O liquid. Those would be the three things in water. Reduction at the cathode. What can I get reduced? What can we reduce? Well, we could potentially reduce sodium, Na plus aqueous, plus an electron going to sodium metal. And that cell potential is negative 2.71 volts. And the problem with sodium here is that we know Na violently reacts with water. So that's not going to happen, right? It's not going to be, sodium metal is not stable in water. Not going to happen. None of the group 1 metals are. What's the other option we have at the cathode here would be water. And we look it up, it's 2H2O plus 2 electrons going to H2 gas plus 2OH minus. And that standard cell potential would be negative 0.83 volts. And so we'll expect this to happen because it's the least negative E standard. It doesn't look right. Let's do that. Negative. Yeah, there we go. What about oxidation at the anode? Well, we have two options. I have 2Cl minus or 2H2O. So 2Cl minus could go to 1 chlorine and 2 electrons. That E standard, if we look it up in our standard reduction potentials, is negative 1.36 volts. Water would go to O2 plus 4 H pluses plus 4 electrons, and that E standard would be 1.23 negative. So we would expect this reaction to occur. Oh boy. However, this is fun. The oxidation of water to oxygen gas, to oxygen gas is slow. All right. Why is it slow? It has a high EA, activation barrier. High energy required to do so, which means it requires an additional overpotential to get the reaction to proceed at a reasonable rate. This is a kinetic effect, which means it's not thermodynamic. Also, the concentration of chloride affects the rate. So there's two controls over a chemical reaction, right? We talked mainly about thermodynamic control, and we started this chapter out about thermodynamic control and what makes delta H more negative, and it's a more stable arrangement of the electrons. There's still that kinetic control that's still there. And in this case, even though thermodynamically speaking, it looks like oxidation of water to oxygen gas would be the way to go here, it doesn't happen this way. Right, so if the oxidation of water is desired, then use an ion that is less easily oxidized than chloride. Such as sodium sulfate. So in this cell, reduction of water would be 2H2O plus 2 electrons going to H2 and 2 hydroxides. Put my state symbols in. That standard cell potential is negative 1.2, no, it's negative 0.83 volts. And the oxidation of chloride happens. So we have 2Cl minus going to Cl2 gas plus 2 electrons, and that cell potential is negative 1.36 volts. So the overall reaction would be 2 waters plus 2 chlorides going to chlorine gas plus H2 gas plus 2 hydroxides with a cell potential of negative 2.19 volts. And that's fun. I usually bring out in class right now the fact that in swimming pools, and where I live there's lots of swimming pools, right? We usually rely on dichlorine or chlorine-based compounds, such as calcium hypochlorite, to destroy the microorganisms in our swimming pools. In fact, the most potent disinfectant is hypochlorous acid. And so in many swimming pools, you actually have this going on, where you have Cl2 gas, or it's actually going to be aqueous in this case, plus water, going back and forth with H plus, Cl minus, and HClO. And that's very nice. That kills all those microorganisms, which we want to be killed. And then to neutralize the hydronium, sometimes we add sodium carbonate. Sodium carbonate would do that, right? So we'd have the CO3 2 minus plus the H plus going to HCO3 minus. Okay. And so we always adjust the pH because it matters. You know, hypochlorite's a base, hypochlorous acid is an acid, bicarbonate's a base, so you gotta keep that in mind. All right. Now, one of the things that is a problem is HClO aqueous, upon sunlight, UV, right, we get 2 HCl and O2. So it breaks down. And so we got to maintain the amount of hypochlorous acid in there in the pool that's safe for swimming, but also kills the microorganisms. Now, a lot of times, what's this one? We think we have the eyes, when you guys open your eyes in the pool, it's usually blamed on too much chlorine, and most of the time that's not the case, right? It's usually the problem that causes the eye irritant would be NH2Cl from the ammonia-related compounds from urine or urea. And so if you look at ammonia, it's dissolved in the pool, plus hypochlorous acid, you get NH2Cl plus H2O liquid. So a lot of times we add more dichlorine and superchlorination to stop this. And also they try to use ozone, all right, but it's a problem. But we stop this with this reaction with the superchlorination and H2C plus chlorine gas goes to N2 gas plus 4HCl. Then you neutralize the pH. And so that's how you get rid of that. So a lot of times open your eyes and it means there's not enough chlorine in the pool and there's a lot too much sweat and other things in the pool. And so the reason I bring all this up is saltwater pools do this reaction we just talked about, pretty much. Right? And saltwater pools have a constant amount of chlorine so that this problem with the amines do not happen, which is kind of nice. And so I don't have a pool at this point. They're not cheap. And so I do want a pool, and I probably will go with a saltwater pool, but depending on the technology, by the time I get one, who knows what's going to happen. It constantly advances. That's why I love this country. One of the reasons, at least. But this is what happens with swimming pool chemistry. I always bring this up in class because it's always fun to talk about what we are. Oh, it's too much chlorine in the pool. Probably not. It's probably not enough chlorine in the pool. And kind of how it works. The next topic we want to talk about would be the stoichiometry of electrolysis. So when we put these, whether it's a swimming pool or something else we're going to talk about, when we put these electrolytic cells in place, we can actually measure or count the electrons. All right. And so what are this? So Faraday's laws. All right. So he has two that we'll write out. The amount of substance liberated or deposited at an electrode is directly proportional to the quantity of electrical charge passed through the cell. So there's a direct proportion to how much charge to how much mass, or how many moles. And for a given quantity of electric charge, for a given quantity of electric charge, the amount of any metal deposited is directly proportional to its equivalent weight. So let's talk about our units. And this makes a lot of sense with the units. And so if we look at amps, if I have something called an amp or A, and that would equal a coulomb per second. It's a rate. Right? So coulombs equals my amps multiplied by my seconds. And also, there's 96,485 coulombs per 1 mole of electron. So if I have time and I have my amps on my charge, I can figure and I can get the mass. Okay. So for example, I got a picture of this as well. There's the hydrolysis of water, or the electrolysis of water. Let's talk about silver plating. So this is electrolytic cell for silver plating. I have silver metal and I have an object to be plated. And so I have a voltage source. So what happens is that voltage source, we actually drive electrons to the object to be plated is the electrode. Right, that's the object to be coated. And silver goes from Ag to Ag plus an electron. And over here we go from Ag plus the electron going to silver metal. So we take the silver from this electrode to the object. All right. And we can actually look at that. So we're driving, see the negative terminal, they're driving electrons to here. You have a salt solution, right, so that the current can keep going, and that's what happens. And so if we do an example of this, all right, and I always use this because I know my wife does this. She likes white gold. She has a white gold ring. A lot of people like white gold. Problem is gold's gold. Gold is gold color. We know what gold looks like. White gold, then, how does that happen? Well, it's rhodium plated. It's actually rhodium plated. So you get your container here, and there's some rhodium. Use purple for rhodium here. There's my rhodium metal, and that's connected to your battery. And you put your gold ring here. And what happens is the rhodium is going to go there, right? So rhodium, what are my equations? And so rhodium RH going to RH3 plus 3 electrons, and then RH3 plus 3 electrons going to RH. And now, why is it evenly coated? Because the least, right, the more distance the electron travels, the more resistance. So it's going to evenly coat because that's how the electrons are going to flow that way. It actually works out beautifully. All right, so we're going to plate this ring. The question then is, what do we know here? So we got a 30-minute flow. I have a 30-minute flow and a current of 5 amps. Well, that 5 amps, if we remember, 5 amps is 5 coulombs per second. And now, once we know it's 5 coulombs per second, 30 minutes is, so right, we have a rate, we have a time, the amount. So 30 minutes, we know that there are, in 1 minute, 60 seconds. And then we know for every 1 second, there are 5 coulombs. And then we know there are 96,485 coulombs per 1 mole of electrons. And I'm telling you it's rhodium 3 plus in this case, so we have 3 moles of electron to 1 mole of rhodium. And then finally, 1 mole of rhodium happens to weigh 102 point, looks like it's 91 grams of rhodium. So if I do this math, looks like I get 3.2 grams of rhodium. That's fun. Another way. What current would deposit 500 milligrams of rhodium? It passed through an electrolytic cell for 5 hours. Again, we're going to tell you that rhodium. Going to rhodium. All right. Okay, we got the time. And so we're looking for what current. What current? I need to know how many coulombs per how many seconds. Well, 1 second. So it's going to be coulombs per 1 second. So I know how many hours. That's an easy one. 5.0 hour, right? And we know that in 1 hour there are 3,600 seconds. So that's 18,000 seconds. So we know the time. Now we have 500 milligrams of rhodium. Well, for milli, I'm just going to write times 10 to the negative third grams of rhodium. And we know, we just did it, 102, right, 0.91 grams of rhodium is 1 mole of rhodium. And we just learned that 1 mole of rhodium, 3 moles of electrons. And for every 1 mole of electrons, there's 96,485 coulombs. So that gives me my coulombs. It looks like it's 1406 coulombs. So my amps will equal my coulombs per second. My coulombs will be 1406 coulombs. And the seconds would be 18,000 seconds. So it looks like my amps is 0.078 amps. So that's Faraday's law. And the only thing that we got to remember really is amps are coulombs per second, and then the conversions are pretty straightforward. Let's talk about corrosion now. And corrosion is the usually gradual and often undesired oxidation of metals or other compounds that are exposed to oxidizing agents primarily O2, but there's other ones in the environment. So oxygen gas, O2, making a reduction, right? O2 gas plus 2H2O liquid plus 4 electrons goes to 4 hydroxides. Notice everything's aqueous here, or gas. E standard is 0.40 volts. Now, in acidic conditions, because obviously that's basic conditions, in acidic conditions. And why would we suggest that most of the planet has acidic conditions? Well, water, as it's coming down, plus CO2 gas, which is natural. And I know that there's this huge thing about being green right now and CO2 emissions, which I'm not saying anything about. I'm saying that if without carbon dioxide on the planet, one, we'd be frozen, and two, there'd be no plant life. And so we definitely need to have CO2. So there's CO2 in the atmosphere, no humans, still CO2, and it's a natural process. So all rain is going to be slightly acidic with carbonic acid and air. All right, all rain has this process going on. So even take all the climate stuff out of the picture, take any emissions out of the picture. 5,000 years ago, rain was still naturally acidic. Right? I don't want to get into the climate debate. I'm just saying this is a natural process. And so in acidic conditions, what happens is O2 gas plus 4H plus aqueous plus 4 electrons going to 2H2O liquid, and that standard cell potential is positive 1.23 volts, which is a lot more of a potential to happen. All right, and so when we say acidic conditions, we're not talking the pH is like dangerous to touch. I'm just talking pH of 6, right, where we have an order of magnitude more H plus than OH minus. All right, that's fine. Most of the time, pH, acidic rain, acidic 5 is the number. So below 5, pH below 5 is when we're worried about it. So pH 6.5, 6.2, we're not worried about that as a lake. Fish are fine. Things are growing fine. It's just this process happens. So if we look at iron, the first one of our building materials, steel. Right? We've been using iron for a long time because it's abundant and cheap. Goes to Fe2 plus 2 electrons, and that's cell potential, negative 0.45 volts. So if I flip that around, or that's the oxidation of iron. So add these two up, and we'll get a negative, or we get a positive E cell, which means it's spontaneous. So if we notice, like if we talk about the rusting of iron, I got a picture to show you in a second. If we notice, moisture must be present for oxidation to occur. That means if you live in a humid environment, like I do, very humid environment, things rust very easily. All right. And moisture must be present because H2O is a reactant. So if you live in a very dry climate, desert area, rusting is less prevalent. Doesn't mean it can't happen, but it's a lot less present. Also, charge must be able to flow between the cathode and the anode, or the anode and the cathode. So we got to have charge flow. So we got to have an electrolyte. So for example, if there's an electrolyte, if we add an electrolyte, such as sodium chloride, right, this enhances current flow. Right? And so I live by the ocean, and the motors of these inboard boats, they have to have saltwater engines because saltwater is corrosive. And all saltwater does is provide this electrolyte that allows the electrons to transfer. The salt doesn't do anything, it just carries the charge. It just charge helps be carried. And so if you have a freshwater engine, you bring it to the ocean, it's going to rust pretty quickly. If you got to have to constantly clean that out with fresh water, it's not worth it. Another thing that happens if you live or are from a cold climate where water freezes and there's ice and snow on the roads, they put salt down on the roads. This helps promote your car to rust. All right. All right. A lot of times coastal climates, there's salt water mist. So that means things around will rust, whether it's your car, whether it's metal near the beach. This happens. All right. Acids help promote rusting too, because if it's acidic, acids help promote rusting. Think about how big of a problem this is for all the international or any type of waterway shipping with iron boats. This is a big deal. Dry dock where boats get pulled out have to be sandblasted and repainted, right? Because there's barnacles that grow on these ships. There's scratches in the paint. And so all these things need to be maintained on these major ships. And to take a big boat out of the ocean is hard. It's a lot of effort, a lot of money. So let's look at rust. It's actually a couple-step process here. So there's a nice picture of rusting on the left. And, we got iron going to iron 2, then iron 2 going to iron 3. So it's actually a couple-step process. It all happens in the water droplet, so to speak, if it's wet. So that's why if you have like nice stainless steel knives, you always want to dry them pretty quickly so that there's not water on them that can promote rusting. And obviously it's acidic, but this is an example of rust. And I want you to point out right here, this little pocket here, that's where the iron is gone. Now, if we can get this rust off the metal, muriatic acid will take it right off, wash it, dry it. But these pits are still there. The metal's still gone. Like, we don't get that metal back. All right, so we can take the rust away, but we don't really get the metal back. You'd have to use electrolysis to get the metal back. And I'm not sure if it works so well. I'm not a metallurgy guy, so you'd have to do more research on that if that happens. But this is gone. So if your grill's rusting, it's right, those grates and stuff, those burners, they're missing mass, so they do become weaker and break. The question then becomes, how is corrosion prevented? How is corrosion prevented? That's a good question. Well, the first easiest way to do things is paint. We paint them. All right. Paint's nice. You paint your cars, this is why scratching paint in cars used to be such a huge deal. It's still a big deal, but it used to be major because cars used to be always steel or sheet metal. So a scratch would start rusting. You open up the sheet metal to rust and it start rusting and fall apart and not good. Now a lot of cars, the bodies are made of plastic, and so they don't rust as much. You still don't want to scratch the car, but it's not as catastrophic to the integrity of the car. Another thing that we do is galvanization. And galvanization is a zinc coating. So zinc is oxidized easily. So zinc is oxidized to ZnO. Here's the thing though. Zinc oxide acts like a protective layer where no further oxidation can occur. So zinc oxide, it makes this layer around the nail or whatever object we're talking about, and as long as you don't scratch off that layer, it's pretty impregnable. It's pretty nice. Aluminum does this too. Aluminum has aluminum oxide, does a layer pretty well. Now, salt areas can still cause aluminum to oxidize, but these, because of how the zinc oxide, the shape of the the lattice is, it prevents further oxidation from occurring. It makes a barrier. It's kind of nice. So you see a lot of galvanized thing at the hardware store. And 3, another thing that we could do is a sacrificial anode. So thinking, go back to zinc. Zinc is pretty cheap, and get a zinc puck or a zinc plate. You put them in the inside of the ship hulls, so that if there's going to be rusting done in the ship, the anode of the zinc will be oxidized and not the ship. So the ship won't rust. The zinc sacrificial anode will oxidize and be decomposed. That saves you a lot of money and time. You could do this on your grill if you wanted to. I had a student who got a plate, metal piece, and put it on his grill. Screwed it on, and it oxidized, and not his grill. His grill didn't rust for a long time. That was pretty neat. So sacrificial anodes, these are really good for things that you can't access. So think about like pipes underground. If you have a big pipe underground, we can't really access it. We can't really, dig it up all the time and look at it. So what they do is put sacrificial anodes that you can easily replace down along the pipe, and you can help prevent the oxidation of the pipe that way. Right? Because this is a big problem, right? Corrosion is a big problem. And material science is still, it's still a big, big area of chemistry, big area of research. I'm just looking at, I'm using an electronic device to do this. You talk about, computers, cell phones, all the electronics that we have, and corrosion in there we don't want. Water's a big problem with them. This is still a big field, and it's, if you're interested in it, it's definitely something that's going to be there for a long time, because again, as long as we're using materials and there's oxygen on the planet that's going to take electrons, right? This is a problem that we're going to have to deal with, for our existence probably. So it's a good thing. That, ladies and gentlemen, concludes day 31. Hopefully that works for you. Hope it was very informative, and we'll see you next time. Take care.